My name is Andy Ross. I'm a software engineer at Google. I've been working on Zephyr for a good while now. I think it's actually close to 8 years. Actually, maybe slightly more now. Sort of all over the bottom layers of stuff, mostly in the kernel, SMP, that sort of thing. But what we're here talking about today is kind of the intermediate layer, the glue that lives between my world and the app layer, and that's interprocess communication. It's something that's been historically pretty varied within Zephyr. We've got a lot of choices. We've got a lot of stuff going on. And it's a real common problem is that people come to places like Discord and have questions about what goes where and what's supposed to work and what is this tool for. And I thought it was probably time for a kind of quick discussion about kind of like where we are and where I think maybe we want to be and what we want to be pushing people towards. Needless to say, Zephyr has a lot of tools in the box. It's a mature system. Mature systems are great. We've been doing this for a long time. We're real confident about the system. We've shipped a lot of products. It also means we've kind of veered down some interesting cul-de-sacs along the way, and so there's some archaeological evidence of those eras that we'd like to have some documentation of. That leads to a bunch of developer choice. That you've got a lot of things you can pick. Too much choice, especially too much choice, without a lot of guidelines in new apps and new markets, tends to lead to bad decisions, missed opportunities, things that you might have done better. And it's important to recognize that Zephyr it's still a real-time operating system. We're still in RTOS. We still care about small systems. I mean, our roots are in really tiny systems, like 4K RAM kind of things. And we tend not to play in that sandbox much anymore. But we're still much smaller than other systems people are going to be coming from that need to deal with these same problems. I mean, like the biggest systems we've got right now are order of 16 megabytes or so. Like the audio DSPs that I tend to work with, most of them are quite a bit smaller. People need to worry about code size in Zephyr, and having lots of choice and lots of things you can link in and lots of stuff you can use tends to lead to larger binaries that nobody really wants. So the sort of basic, audience for the talk, who's supposed to be here. I did promise this was going to be intermediate level. We're not going to talk about assembly language. We're not going to talk about architecture layer. We're certainly not going to talk about hardware. This is all C code, hopefully. Try to hold me to that. So it's people who are like familiar with Zephyr and really want to see like deep dive into the weird stuff that they've seen or maybe noticed or wondered about. People from other systems, like any Linux folks wandering in here who are just curious, might like a tour of how smaller systems, different systems might do the same stuff that they're used to seeing. And really just anybody who might be curious about concurrent programming in general. Things that we all like to think we know about, and pitfalls and traps that we've all made and we've all learned from. It would be good to at least have somewhere in a Zephyr context we can kind of call that stuff out, because I guarantee we all make those mistakes every week. So why is there an IPC layer, right? I mean, IPC is interprocess communication, right? We have IPC because we have threads. Zephyr's got threads all over the place. That's really the core abstraction that we're providing to the users, is that you can take your code from wherever else it is in the world as a nice sequential algorithm and bolt it into your system and just run it, do this and then this and then this and then this and then this, and get to the end and be done. And that's the way that we all like to write code, because it's the way we all understand. Except in big modern systems, there's lots and lots of components that need to do all of that. So the natural way to do that is that you do it with a thread. That means the natural way you do it is with a whole bunch of teams running in their own threads or with their own ideas about how it works. And once you've got threads, you've got parallelism. Once you've got parallelism, you need synchronization. You need ways to get the threads to work with each other so they don't step on each other's feet. And that synchronization is just a hard problem, and we'll talk some about that today. IPC just provides simpler tools than the very low level, here is how you synchronize two threads running in shared memory. It gives you different metaphors that are easier to reason about. That's the fundamental idea here. And in fact, the core metaphor, and this is the closest I'm going to get to actually defining IPC, because I don't think there is a good definition for this stuff. IPC is about wait until, right? It's the idea that you've got a thread, it's going to do something, it's going to continue to do something until the end of time, because that's the way computers work. And you need a way to say, no, stop, you're not ready yet. It's not done. There's nothing in the queue. new, there's no command ready, the network is silent, you know, something has not happened that you need to wait until. In fact, I got ahead of myself with the why so many threads. I already covered most of this law, but again, it's important to recognize that we have the lots of threads for reasons that may not necessarily be great design, but are unavoidable. We've got big teams, we've got lots of stuff, we've got things from different sources. The core value Zephyr is providing here is that we give you a way to organize all of this stuff, and threads are an important idea there. And so how do you get, you know, now you've got all the threads, you know, what naturally happens here is that people tend to try to bolt stuff together, and if you don't have IPC, you kind of can make things work, and there's a little bit of source sample code here that is kind of showing the sort of thing that I think we've all done, we've all seen. You know, generally it's some variant of polling, right? You've got something that needs to happen, and in here it's, you know, something to do is a predicate, and you're going to call that, and then you're going to call do something. And if you do that in a fast loop, typically what you see happens is nothing happens because you're the highest priority thread, and you're sitting there in an infinite loop, and so nobody else is going to run. If you're lucky, maybe, you know, something to do is being filled by an ISR somewhere, and so you might actually notice it happen. Then people try to you know, fix it by throwing, oh, let's throw in a yield. You know, like you look at the scheduler docs for Zephyr, and you see that, yield gives other threads a chance to run. You throw that in. You realize that yield only really works for threads at your priority. So you end up then throwing a sleep in. All right, fine, we'll just sleep. It's fine. You have 20 milliseconds. It's not a big deal. We know that that's our budget anyway. It'll work. Excuse me. Then you realize that 20 milliseconds doesn't actually work because sometimes you're missing one and you're not really sure why that happens because of aliasing and the timing. So let's do it in 10 milliseconds instead. This is clearly not the way we do things. This is the problem we're trying to solve. But it's important to recognize too that this is tempting, and we'll come back to this kind of code later on because it tends to pop up in places where you don't really expect. Again, giant problem area. Lots of stuff to talk about, so I think it's important to have a slide on the stuff we're not going to talk about. IPC obviously is a big kind of, you know, abstract conceptual idea. It doesn't only come from the kernel. The kernel obviously needs to provide a bunch of tools, but there's a lot of other stuff in the world that is dealing with the same problems. You know, there's lots of framework code in Zephyr, some of which is quite large, some of which comes from other environments, and they've got their own ideas, right? Like, you know, there was just a talk on ZBus, which unfortunately I missed, but I'm going to go watch it later on, which is a rather higher level, you know, RPC, you know, remote procedure call based way to connect stuff together. Looks great. It's probably something to consider. I'm not going to talk about it. The network layer obviously has its own built-in IPC, and some of that is historical. You know, obviously the network code, you know, arrived very, very early on before a lot of the stuff that we're talking about today was really mature enough. And also the network code is implementing, you know, BSD sockets. There was a pre-existing API to do what you want. That doesn't work very well with a lot of this stuff, unfortunately. It would be good for that to converge at some point in the future, but again, not going to talk about it. And then there are things like, you know, we've got a SimSys abstraction layer that provides wrappers around, you know, semaphores and mutexes and that sort of thing. POSIX we have too, but we will talk about that a little bit. We're not going to talk about frameworks. And then at the very bottom, recognize that this problem is also solved without kernel interaction at all. And we're developing a big stable of good tools out there. You probably want to take a look at the single producer, single consumer, multiple producer, single consumer tools are lockless message passing things that have no kernel interaction at all. They look really great. WinStream is a similar idea for byte streams. I wrote that one. That was actually for cross-host logging from the Intel DSPs, where we cannot send an interrupt to a Python script on the host, so therefore we can't use the base logging. And needless to say, lockless algorithms like totally out of scope. We're not going to be talking about that at all. But do recognize there's a lot of stuff aimed at the same problem area. And then a final caveat is, you know, well, what if we don't actually want all those threads, right? Threads are really expensive. There's probably the most expensive single data structure you're ever going to deal with in the kernel. can you get rid of them? And the answer is, yeah, you can. You can totally do it. That's what a work queue is, right? We have a system work queue that's kind of provided by default. It does exactly what it says. You give it a callback, it'll call that callback in order, in the order in which they were inserted into the queue. It's got some other features too. It'll take a delay for each work item. Work queues are simple, they're straightforward. They're used by a lot of subsystem codes, so they're fairly cheap. That is to say, you're probably linking in the system work queue already, and if you are, you don't take any extra code size to use it. And because they're in order and one at a time kind of things, there's no there's no decision needed on until that we were talking about earlier, right? That's, you don't have a thread, so you don't need to wait. You just got to do everything you've got. And this is async code, right? I mean, like this is all the rage out there in the rest of the world. More elaborate environments out there, starting with JavaScript about 15 years ago, and now like Python and Rust are into this kind of thing too. Have big elaborate syntax-based frameworks around that. Unfortunately, we don't. Work queues, you're going to pass it a callback. It's a C function pointer with a closure where there's the void star argument. So we don't have the level of glitz that these other environments do. But as a synchronization problem, it's appropriate, and it's appropriate for exactly the same reason. So do consider it. But again, that's not really what we're talking about today. And then the final point there is just to point out that there is a work queue just does everything in order, right? So all of the RTOS features that you're used to about controlling latency and priority and all of that stuff have nothing to do with work queue items. The very last point is there is actually a P4 work queue in there, totally out of scope for this talk. I wrote that a couple years ago, which basically turns the work queue items or work queue-like items into little threadlets. They've got their own priorities and can preempt each other. It's good to look at. Go take a look. So how does this actually work? All right, so we've got a problem, and we've got to have a solution in the kernel. The kernel provides the IPC layers as the top layer. It's got to have something to do on the bottom. And the first thing, of course, you need for any kind of parallel environment, and everybody learns this in school, is mutual exclusion. You have to have the idea that you're going to be looking at some data. What that data is not, really the problem of the framework. You're going to need to look at it, and you're going to need to say, hey, I know for sure that the picture that I'm seeing right now and the values that I'm computing are not being seen in a different state by somebody else somewhere else that's going to make a different decision. So you do that with a lock, right? And everybody's seen that, right? You do some level of locking. We've got actually a bewildering variety of locks at the bottom level of the kernel. We've got sched locks and all of that stuff. But at the very bottom layer, this is always done with a spin lock in Zephyr. And a spin lock is well, actually, on a single CPU system, a spin lock is nothing. It just masks interrupts and goes on. On an SMP system, it's got more work to do. So it's got there's a single bit of information telling you whether it's locked, and it'll sit there and spin on that until it's available, and then atomically take it and move on. The spin lock is not the API we're talking about right now, but it's important to recognize that that is the API on which all of this is based. There was a great discussion about ticket spin locks yesterday, if folks saw that talk. So this is, it's evolving as we move on, and it's the kernel's basic idea. But it's not a great choice for apps, right? And why is it not a good choice for apps, right? It's well, the big one is it doesn't work in user space, right? It has to mask interrupts as just a native abstraction that it's dealing with. Since it can't mask interrupts in user space, you can't use it in user space. We'll talk about it. There's a POSIX one later on. We'll talk about it a little bit. If you're not careful about it, obviously you've masked interrupts. You're going to cause latency problems. You're going to block out interrupts. In the kernel, where we kind of mostly trust ourselves, sometimes sort of, we take that as just a design point and make sure that our critical sections are small. That's a real heavy burden to use with apps, especially when you're calling into things like third-party code that may not be as careful. So not a great choice for apps. So we'll come back to that in just a moment. Second basic building block, and this is the sort of more important one from the kernel's perspective, is blocking inside of Zephyr. If folks are familiar with the kernel code, we actually use pend as the verb and not blocking. I'm going with the Unix term here because I think people are going to be more familiar with it. The thread can't be running all the time, right? Like computers will run in perpetuity forever. You need to let other threads run. You need to stop them. So the kernel has the ability to stop a thread, right? You context switch out of the thread, you take the thread pointer, and you stick it into a list, and we call that list await queue. That's really all it is. It's just an ordered list of threads. There's a little more complexity in that we sort it by priority order, so when you wake up somebody who's waiting on it, it wakes up the highest priority one. There's a little bit of fanciness to the back end. We can store that as just a simple, doubly linked list in order, or we can store it in like an RB tree. If you want to have like 100 or 1,000 threads waiting, if you have the memory budget for 1,000 threads, we can do that algorithmically fast. And really, that's all about there is to say about the data structure. And then behaviorally, it's works like you expect. You pop it off the list, stick it into the list, it'll sort it into the list. The only gotcha though is that it must be called when holding a spin lock, and it will release that spin lock atomically with the placement of your thread into the list, and that's to eliminate what is a fundamental race condition we'll talk about in just a bit. And it also takes a timeout parameter. And this does exactly what you think. It's like you're going to go to sleep, but you want to wake up after some amount of time. You can pass K forever if you want to sleep forever. You can pass K no wait, which means return instantly even if you aren't going to do whatever it was you wanted to do. This is a way to represent like non-blocking I/O and that sort of thing, which in Unix typically is a little more complicated or a little more API specific. In Zephyr, it's just one parameter to one utility, and then it gets percolated up. Basically, everything in Zephyr you're ever going to do that's going to block, it's going to take one of these parameters, and you can specify whichever timeout you want. The other good thing for about K no wait, I should mention, is that it allows you to work in an ISR context. It's a natural way to say, hey, do something like insert into a pipe that might be full, or down a semaphore that might be empty, that sort of thing, and then return instantly with an indication that the failure happened instead of having to block. Because needless to say, in an ISR, you can't block. You're not a thread. And again, the final point, just pointing out that other operating systems have this kind of thing, but it's a little bit kludgy, right? Unix select and polar allow you to do this on arbitrary file descriptors. Read and write don't have that idea. Sockets have timeouts that you need to specify as options at the network stack layer. We put it all in one place. I think it's one of the nice thing we do. So now let's finally talk about an application visible IPC primitive. That is KSEM. Most people are familiar with semaphores. You learn about them in school. I'm just going to zoom really super quickly through. A semaphore is an abstraction of the idea of a queue. Something is going to happen, right? You're going to take I call it a token here. You're going to stuff a token into the semaphore. The semaphore is going to say, okay, great. Well, is anybody waiting on a token? I've got three threads that are blocked here. It's going to pull the highest priority one off, run it. If somebody comes in with another token, or another, or a third, or a fourth, it'll just keep counting up, so that if 4 threads come by and you've got 5 tokens available, they'll all get to run. And if 7 threads come by and you've got 4 tokens available, 4 of them get to run, and then 3 of them block. So it's kind of like a queue. Each token that goes through is one person that gets to wake up. And again, I'm using different terminology here, but you notice that the read kind of encapsulates that wait until idea I mentioned with IPC, right? You go to the semaphore, you down your semaphore, which is the term I'm using here. Zephyr calls it take, and you will block. If there's nothing available, you're going to stop. Again, historically, the naming, as I mentioned, is kind of awful. The original semaphores were defined by, I want to say it's Dijkstra, is that right? But it was V and P were the original operations. Up and down is more common. That's what you see in the Linux kernel. Post and wait. I don't know that I've ever seen that anywhere else, but it is in fact the System 5 semaphore API. Zephyr uses give and take, which again I think is unique to Zephyr. I don't think anybody else does that. Doesn't really matter. Most of those are fairly clear. You see some sample code here. You'll see this again and again and again throughout every system, every subsystem in the Zephyr tree. It's really pretty straightforward. There's an error code obviously for KSEM take, because that's a blocking operation. There is no such error code for KSEM give, because that is not a blocking operation in the semaphore. We're going to talk about that in just a second. Use semaphores everywhere you want to. They are fast, they're small, they are fair, and I'm putting that in scare quotes because there's a digression here that is scheduler specific, but not really IPC specific. When you do something in Zephyr, almost everywhere that is going to change the scheduler parameters, change the idea of who's going to be most runnable right now. Like for example, you give a semaphore and somebody higher priority was waiting on it. Zephyr is going to do a synchronous reschedule. That is not universally true everywhere. There are exceptions, but semaphores are not one. Semaphores are what are called a fair semaphore. That's not always what you want. Occasionally there are performance benefits to waking somebody higher priority up, but then finishing your task for cache residency reasons, or because you're about to wake up somebody even higher priority before going on. But that is the way that the KSEM works. and the big one is it's already there. Like, I mean, there are semaphores within the kernel. There's semaphores in almost every subsystem. The incremental linkage cost of using a semaphore in your own code is basically zero. Use a semaphore. If it's appropriate to your problem, you know, don't pause. Don't worry about what the best choice is. Use a semaphore, and it includes on things that aren't necessarily semaphore-related problems. You see this pattern pervasively in Zephyr, right? You take a semaphore, you set its count to 1, you initialize it to 1. There's some sample code there that shows you how to do that. Or you could just, you know, do a ksem give right after you initialize it. And then ksem take, you know, decrements the count from 1 to 0. That is a non-blocking operation. You're going to return instantly. The second person tries to ksem take, and they're going to block. Then you ksem give, and that wakes them up, and they get to run. That now has become a lock, right? It's one-to-one analogous with any mutex API you're ever going to see, and it's based on semaphores, so it's incredibly lightweight. And Zephyr uses this everywhere. I think this is a great pattern. Again, it has that benefit that because semaphores are already used everywhere, there's zero overhead. It's super fast. Ksem take in the uncontended case where there's already a count in there is dozen cycle kind of thing. It's, you know, it's really very, very fast, maybe 20 cycles. It depends on your hardware, right? But all it needs to do is, you know, go to a single address of memory and decrement it, and there's a spin lock around it. So, you know, like 2 interrupt mask operations, and you're decrement and you're done. It's really only slightly slower than a spin lock, and in fact, on SMP platforms, because of this, if it's a contended spin lock, there's a relaxation step we need to do that can actually be getting, like with Intel ADSP is now up to, like, you know, hundreds of cycles of relaxation required. So in fact, semaphores may even be faster on some systems. So use this, like if you know, again, if you need a lock around something and you're not in a level of code sophistication, like not developer sophistication, but there are just some places you don't want to use a spin lock, right? If you can use a spin lock, use a spin lock. Spin locks work basically everywhere. But if you're in user space, or if you're in library code that's going to need to call into some arbitrary thing that's going to need to do a lot of stuff, and you need to have a blocking lock, this is the one you should be looking at first. We do, however, have a dedicated mutex primitive. Kmutex is there. It does work. It's good. It does everything that the spin lock that I just mentioned does, plus better error checking because it can detect the misuse problem. What if you give the lock more than once? You can end up with a lock that has a count of 2, and now you can have 2 people hold the lock. That's really bad. It also provides priority inheritance, which is a really cool RTOS feature where the circumstance where you're going to need this, right, is you've got here, okay, somebody goes and takes a lock, right? Low priority thread takes the lock. A higher priority thread comes in, preempts the low priority thread, and starts doing stuff instead. Now the low priority thread isn't doing anything. A higher priority thread comes along and needs to block on that same lock. It won't get it because the lowest priority thread has it already and won't run because there's a medium priority thread that's already blocking it. So you need to bounce down 2 layers to give the lockup to get back up to this one. But that won't happen because, in fact, the middle layer is going to run instead. Ergo, it would be kind of nice if you could grant your priority to the owner of the lock so they can get their stuff done really fast. It's a good feature. It's not that good a feature. It results in a larger, slower, bigger. Again, this is not used by the rest of the subsystem, so you're going to be paying linkage cost to use it. Larger, slower, bigger abstraction. And the truth is, PI is really only useful if all the blocking in your system is done on a kmutex. If your high priority thread is blocking on a semaphore, if it's blocking on a pipe, if it's doing some other IO that's going to enter a wait queue in the kernel, you don't win for this. So it's harmless. It works fine. Certainly don't refuse to use this. But again, within Zephyr, the overwhelming pattern is to prefer ksem for this application. And you might ask, why don't we have an abstraction around ksem to do that? And I don't have an answer for that. We probably should. So now we're moving on to the rest of the stable here, where things start to look like a lot more overlapping. So the idea is that we've got this wait until operation, right? We're going to wait until something is ready for the semaphore. Wait until someone has called ksem give. So the semaphores do that part on they do that blocking on the read part, right? The wait until. But what if you've got data, right? You're going to stuff some data into a pipe message queue, something like that. Well, that might be full, right? So you actually need to be able to wait until there is space in the queue too. So there's a little bit more work here, but it's the same basic metaphor, and it works really well. And there's a quick digression here where I'm showing a, a little command line down there at the bottom, pointing out that, like Unix obviously has been using file descriptors since the beginning of time. As like the universal process interop abstraction. And so down there we've got, a little command line. I think folks probably recognize what that does, right? This is going to tell you who's given the most commits to a Git archive. But think about what it's doing. It's 5, right? 1, 2, 3, 4, 5 different processes. They're all like separately launched, separately spawned, doing their own thing with different code, in some cases to APIs that were specified decades apart. And in fact, they're on modern systems like this 12-core, monster mid-range Chromebook. They're all running on a physically separate CPU. And yet they're talking all via just exactly one abstraction. There's only one piece of information. You need to know how to get all of these guys to talk to each other. And that's, of course, the Unix pipe right there. So, I mean, queuing is great. Use queuing. We've got a lot of queues. So we've got like 9. Well, it's not that bad, but it's pretty bad. So I'm going to go very quickly through some of them just to give folks an overview. K50 is the first one you're probably going to see. This was a very, very early one in Zephyr. A lot of the sample code likes K50. It's a great choice for space constrained systems because all it is queuing up is just app managed structs, right? I mean, you've got some memory. In that memory, you need a void star, to have a singly linked list node. And that's really all you need to do. So the kernel doesn't need to do any allocation. It doesn't need to do any space management. There's no buffer to fill up. In fact, which makes a little bit of a lie that you need to have the blocking on write. There is no blocking on write on K50. And it works great. And you can see the sample code here. As a digression, I will note that I'm a little bit contra-idiomatic here. K50 is a intrusive data structure. The way we defined it and the way our sample code works, it typically says you must put the list node at the top of the struct that you're going to insert. So in this case, the myrec struct would have the Q node up at the top. Therefore, you could use the pointer to the myrec directly in the K50 get and K50 put. That's not the way that intrusive data structures work in most of the rest of the world. It's certainly not the way they work in Linux. It's not the way the slist and dlist and rb-tree APIs work in Zephyr. So here I'm kind of like, I'm using the container of macro to give it a Q node, even though you'll see it's a void star there. We don't have a KQ node T struct type. We should, we don't. It's an API wart. So I'm kind of inventing the abstraction here just by calling it a void star. And this is pretty much exactly what you want. If you just want a linked list of stuff and then have synchronization around it to block when it's empty, use this. Queues are great. Queues are very simple. Once you're over the hump of the intrusive data structure stuff, there's not much more you really need to worry about. So use that. It's also worth pointing out that KQ exists in a couple of variants. It's a singly linked list. You can insert it either the tail or the front of the list because you need both pointers in order to do your list stuff. Therefore, we've got a LIFO that is also implemented in terms of the same abstraction, which is basically conceptually a stack. You put stuff in, and it grows bigger, and you pop stuff off the top. But there's linked lists in both cases, and they use exactly the same code. We do have others. There is a message queue abstraction. Unlike the one we were just talking about, this one is not intrusive. You're using fixed size messages. It copies them into a buffer, copies them out of the buffer at the reader level. There's not a whole lot more to say. It does exactly what you expect. Where I was mentioning earlier that you do this blocking on write problem, this does provide that. If you try to write into a full message queue, that's exactly what you're going to get. It's simple, it's reasonable. If it fits your problem, use it. They do need to be fixed sizes, so there's a little bit of extra work. Obviously, the copying of the buffer is extra work. The buffer itself is extra memory to worry about. But in a lot of cases, you do have more dynamic storage management, and the linked list of structs is not as useful. When we get to user space, it's also something the copying works as advertised, so it doesn't have the weird behavior that FIFOs have in user space. We'll talk about that in a bit. Pipes, even more of the same, basically. Pipes are now an ordered stream of bytes. In fact, pipes are more or less one-to-one with a Unix pipe. They do exactly what you want them to do. both message queue and pipes, I should mention, have a zero copy optimization internally. For people who care about performance, if you write into an empty pipe or an empty message queue on which there's a reader, it'll directly copy the data that you're inserting into their buffer. That does make the code maybe more complicated than it needs to be, and I'm not sure that it's always a win for most apps, but it is a nice thing to mention. But it is worth pointing out that these are good choices. They overlap pretty badly. So I would, again, if you're in a space-constrained app, and a lot of us really, even on the big systems, even on audio TSPs, there's still concern about code size. Probably don't use both. If you can avoid it, just use a pipe. Pipes are more general. Pipes are straightforward. There's really very little performance advantage to message queue. There's a little bit of code size if you're only going to use one. So now let's move on. So we've got queues out there, and we're going to come back to talk about queues in the context of poll in a bit. But I did want to go off on one kind of discussion about race conditions that are real common when using these queues. So the basic idea of the queue, right, is you've got stuff that's coming in. You grab your thing, you do it. You grab your thing, you do it. You grab the thing, you do it. It is extremely tempting to have logic around that might condition the extraction from the IPC primitive, right? You're going to read from the pipe only if this condition is true, or you're going to read from this pipe under these circumstances and this pipe under these circumstances. And virtually every time you do that, that is a bug. I've tried to be clever and include some sample code here that does it in a non-obvious way. Basically, this is exactly the sample code you saw before about the FIFO queuing code, but it has a little switch box kind of thing, this set queue thing that can change the current queue that you're using. And because there's no synchronization around it, you say, okay, well, it looks correct because everything is just one line of code, but of course it's not. The load of that curve FIFO value from memory is happening at a different interruptible moment from the use within the kernel that's going to put your thread to sleep. Therefore, the explanation here is that the FIFO can change. That's probably causing a deadlock. Like for example, if you're about to insert something into the queue, and you got your thing, you figure out which queue to insert it into, and then boom, the thing changes. Before that happens, you're going to drop it into the old queue, not the new queue. Maybe it'll be forgotten forever, who knows. There are all kinds of bugs you can have here, but it's a fundamental problem with queuing as an abstraction if you're going to put this logic around it that says, which queue to use, when to use it, how long to wait, that sort of thing. Almost anything you do is either going to be a race condition or it's going to be isomorphic to the polling problem we talked about earlier. And then there's a note there at the end that, well, it sounds just like a data race, right? I mean, you just need to make sure it's locked, right? But there's no place to put the unlock call because that happens down in the kernel. You need to make sure that when the kernel puts you to sleep, you're still locked. But as soon as you're asleep, you can't be locked anymore. And so what do you do? And what you do is condition variables. And again, this is a textbook discussion that I think most people have already seen at some point, so I don't want to spend too much time on it. Condition variables are, in a sense, the most general IPC primitive. You can implement other primitives in terms of condition variables. The opposite is not true. And their basic abstraction is just go to sleep and wake up, just like anything else. But the addition that they've got is that they've got a lock that is atomically released at the moment where you wait. So you've made your decision to go to sleep for whatever reason, and you go to sleep and release the lock without any opportunity for anybody else to get in the way. And that solves the problem, and it works pretty well. In fact, it works so well, we've actually seen it before. Right? The discussion here is about kconvvar, which is a top-level API primitive. But this is, in fact, that spin lock plus wait queue is exactly the same metaphor. And so the kernel is doing this already for you in order to implement semaphores and, in fact, everything else within the system. Yeah, use this. I mean, this is, if you've got a complicated synchronization problem, and some problems really are complicated, this is what you want to use. I mean, and the rules are pretty simple, right? You take the lock, you do whatever it is you want to either decide to wake somebody up or decide to go to sleep yourself, and then kconwait will release the lock for you and go to sleep, or kcon signal to wake somebody up. I don't have any sample code here because there wasn't space on the slide and I'm running out of time. But you do recognize the rules are simple. The implementation really isn't. This is complicated synchronization. You need to do it if you've got a complicated problem. But you need to know that you're in that space. At that stage, there aren't any really easy things. And so is that the end of the story, right? I mean, you've got condition variables, you now got the most common ones. Well, there's one real common case that people tend to see a lot of, that doesn't really need a condition variable, but it does need something. And that's, you've got more than one thing, right? You've got a main loop, right? This is like every app has this somewhere, right? You've got stuff that can happen. It might be, you know, network packets coming in here. It might be keyboard events over here. It could be app-defined timers, you know, upping a semaphore somewhere else. You know, all of this stuff might happen. You just need to wait for the next thing to happen. You don't care which one it is. And a naive way to do this, you don't need a condition variable for this. You don't need anything fancy at all, right? You just have a whole bunch more threads. Each input can have a thread. They then demultiplex into, you know, one command pipe, main loop pipe, whatever it is, and then each one does its own thing. That's wasteful. Most people aren't real happy with that. I mean, again, a thread is the most expensive thing you're gonna ever use. You know, you're looking at 4K or so for a thread stack. So we do provide kpoll. Kpoll does exactly what you expect it to do. It works with a bunch of, but not all of the existing IPC primitives. You can use kpoll signal, which is a user-specified one. There is a gotcha where the others are all level triggered. That is to say, if you call kpoll and it says, okay, this one's available, then you don't do anything with it. You don't read it out. You call kpoll again, you get the same thing. Kpoll signal is one shot. The app is required to have reset it, so you need some logic in order to recognize that you've reset it and that it's still there. It is pretty big and heavyweight. I do include the link to the docs because the sample code is too large. We also have, and I'll go very quickly at this stage because we're starting to run out of time, but we do have K-Event, as is a comparatively new tool from Peter at Intel, which does a lot of what kpoll does, but without a lot of the complexity. It's much, much smaller, much simpler, easier to understand. The name is a little weird. I think it actually comes from FreeRTOS. They have an event group abstraction, which is very similar. It's just got a word. It's just a bit mask of 32 possible events. You can signal any of them that you want just by specifying a mask. You can wait on any combination of them, again, by specifying a mask. And it'll wake you up when any of those have occurred, and then you can go and then poll them yourself. It doesn't, the events themselves are signaled directly from app code. They don't interoperate with existing abstractions, but they are there. And so final important point here, and I think I'm going to get barely through this. What about user space? So the simple answer is everything still works in user space, right? You set user space equals Y. All the IPC primitives become kernel objects, right? They're all living in kernel side memory. They're all just handles that you use. All of the calls become syscalls. Everything still works. The problem is that the performance characteristics of the system completely change. Where I was like, remember I was boosting KSM earlier is like, you know, please use this for a lock because it's like a dozen instructions. Now it's like, you know, change a whole memory map. There's a couple hundred cycles to do that. On some systems there are cache effects. You know, it's a big mess. And so all of a sudden you don't really, a lot of these things about which you might be making these kind of weird decisions about, oh, I need a message queue or a semaphore, none of that really seems to matter anymore because everything is bound up in the overhead of doing the system call in the first place. Which is to say, it sort of starts to look a lot like Unix. A lot of the same intuition about app performance starts to obtain, right? Like, you know, where if you look at standard I/O, like you do a printf from a Unix process, and the printf does not, you know, it's got 16 bytes of output. It does not have a new line in the middle of the stream. Your libc is going to say, you know what, I don't need to call a write system call. This has more stuff coming behind it. I'm only going to flush when I see a new line or when I get beyond my buffer size. All of this sort of thing starts to become more important than the actual IPC APIs themselves. And pipes start to look a lot better. In fact, if you're doing something from scratch, worrying about IPC and Zephyr, you probably want to be using it entirely with pipes. And then final important thread, slide, I'm going to go through some other stuff real super quickly. Is that unavoidable? Like, you know, can we get back to the fast user space IPC we used to have? And the answer is, in the uncontended case, kind of, right? That semaphore, remember we were mentioning, has a count, right? If the semaphore count is 1 and you lock the semaphore by moving it to 0, you don't really need to talk to the kernel to do that, right? You just, you know, just decrement it, right? And somebody else will notice that it's locked. Likewise, if you're upping a semaphore and no one's waiting on it, you don't need to do that. So there is, in fact, a syssem primitive in Zephyr It works exactly like KSEM. Unfortunately, it is different code. It is based on a different kernel primitive called mutex, which, for Linux people here, is basically basically a duplication of the simple modes of kfutex, of Linux futex. It's a little bit slower when you've got no user space used. It is a little bit bigger. It would be nice if it was kind of all the same. And I did try once, and this zinc patch still exists. And if I'm nagged enough, I might try to dig it out. The problem is zinc was, in order to handle all of the various edge cases, it ended up being a little bit bigger than existing KSEM, kmutex, kconvar code. And it was kind of violating its own design point, and it needed a little optimization. There is a sysmutex. Don't touch it. Sysmutex is a wrapper around kmutex. The priority inheritance problem that I mentioned earlier is fundamental, and it requires that the kernel know who owns the lock, and that is not something you can do from within a user space context where you can only change untrusted memory. So you'll end up with the kernel essentially handing priorities out to the wrong people, and so we can't really make sysmutex work. It's there, it does work, just don't use it. That's not something that we're going to be able to deal with. And just blasting through the rest of this stuff. Oh, and Maureen is saying stop. All right, but we do have POSIX. We've got mailboxes and stacks. Nobody wants to use those. And then, well, you can look at the complaints. Mailbox is just simply older. Stacks are weird. You can use stacks. Stacks are perfectly safe. Mailbox is not. Final recommendations, just to sum up the stuff that I think is important. Use the subsystem IPC if that's what your app is based around, right? If you're writing a Bluetooth app, stick with the Bluetooth framework. Don't try to do the interop yourself. Likewise, if you're porting POSIX code, stick to the POSIX stuff. Lean very heavily on the simple abstractions, Semaphores, queuing for other stuff. If you do need to do the multiplexing of inputs, K-events probably preferable to K-poll. Never predicate your blocking calls. We mentioned that earlier. Don't get fancy. And if you do need to get fancy, start with condition variables, because I guarantee that if you're just worried that the fit isn't quite right around a synchronization problem. This is one of these very, kind of rare circumstances in computer science. If it doesn't seem like a good fit, it's actually probably wrong in synchronization. So do worry about that. And then come find us on Discord. Some of these questions are pretty straightforward, but I do find a lot of stuff gets left until code review, and it's good to be able to pontificate in a less contentious environment. All right. And I don't think we have time for questions, so I guess we're all done.